Welcome to Okonko Academy. In today's lesson, we'll be looking at organic chemistry, the basics, that's the general introduction. So today, we begin our journey into organic chemistry. The first lecture as I said, the general uh, introduction. And we are going to cover some foundational concepts that will underpin everything you learn in this course. So, the introduction. The name organic chemistry actually comes from the word organism, as historically chemists believed organic compounds could only be produced by living things. We know that's not true, but the name stuck. Today, organic chemistry is defined as the study of carbon compounds. Carbon sits at position 6 on the periodic table. It's a second row element. While carbon is the defining element of organic compounds, most also contain hydrogen, and many include nitrogen, oxygen, phosphorus, sulfur, chlorine, or other elements as well. Organic chemistry is not just confined to the lab, it is everywhere in our daily lives. Most of the compounds we rely on for food, medicine, clothing, like cotton, wool, and silk, and energy, like natural gas and petroleum, are all organic compounds. And it doesn't stop at nature. Chemists have synthesized millions of compounds never found in nature. Synthetic fabrics, plastics, rubber, life-saving medicines, and even everyday materials like photographic film and superglue. Organic chemistry literally shaped the modern world. So as you can see, these are the examples in organic chemistry. That's the organic compounds. These are the examples I shown. To understand organic compounds, we first need to revisit atomic structure. Compounds are made up of elements combined in different proportions. Elements are made up of atoms, and atoms consist of a positively charged nucleus consisting containing protons and neutrons, surrounded by a cloud of negatively charged electrons. This three-tier hierarchy, compound, element, atom, is the foundation of all chemistry. So as you can see, we need to have we need to have um, compounds first. Yeah. So from compound to element, then from element to what? Atoms. Yes, and then from atoms you have the subatomic particle, the subatomic particles, right? Yeah, subatomic particles. Yeah. Each element is uniquely identified by its atomic number Z, which equals the number of photons in its nucleus. So the identity of every element is its number of protons in the nucleus. For example, carbon has 6 protons, so its atomic number is 6, right? And this number never changes for a given element. It is the identity of that what atom. So yes, since the proton is in the nucleus, so if you have the nucleus, the proton is in it. So it's very high or impossible for the proton to change, the proton number to change. That's why the number doesn't change. So the atomic number is the identity of the element. Take a moment to look at this diagram. So this virtually illustrates what we've just discussed above atomic structure. So pay attention to the placement of the protons and neutrons in the nucleus. The electrons, yes, so the electrons are also there. The surrounding shells, yeah, the electrons in the surrounding shells. So this structure will become very important when we discuss bonding. So basically, this is the periodic table. Yeah, the periodic table. Now let's talk about isotopes. All atoms are of the same element have the same number of protons, and that's what makes them the same element. However, atoms of the same element can have different masses if they have different numbers of neutrons. These variants are called isotopes. Isotopes of an element behave nearly identically chemically but differ in mass. So yes, so if you have atoms, the proton number is the same for all of them, but the neutron number changes. That results in different masses. Like so, that makes them isotopes. Now, let's look at some examples. Carbon has three naturally occurring isotopes. Carbon 12 with 6 protons and 6 neutrons. Carbon 13 with 6 protons and 7 neutrons. And carbon 14 with 6 protons and 8 neutrons. Similarly, hydrogen has 3 isotopes. So this is the carbon one and this is the hydrogen. So hydrogen with 1 proton and no neutrons. Hydrogen with what? 1 proton and 1 neutron. And we have, so that's called the deuterium. And then hydrogen with what? 1 proton and what? 2 neutrons. That's the tritium. Yeah. Now, a crucial concept: valence electrons. Electrons orbit the nucleus in shells of increasing energy. The outermost shell, called the valence shell, is the most important because these are the electrons an atom uses to form chemical bonds. The number of valence electrons equals the number of the elements on the periodic table. Yes, that is very important. This is why group number group number matters so much in chemistry. Yeah. So the valence electrons are the outermost shell electrons, right? And they are very, very important as far as chemical reaction is concerned. Let's apply this, right? Carbon is in group IVA, so it has 4 valence electrons. Nitrogen is in group Va, giving it 5 valence electrons, and the halogens fluorine, chlorine, bromine, and iodine are all in group VIIA, so they each have 7 valence electrons. You will use these numbers constantly when drawing structures, so commit them to memory. Yeah, so as you know, in inorganic chemistry they are very, very important. You'll be applying them in organic chemistry as well. Next, we look at the structural theory of organic chemistry. One of the key rules is that each element forms a characteristic number of covalent bonds. Look at this table, and look at this table, and as you can see here, yeah, hydrogen forms 1 bond Carbon forms 4 bonds, nitrogen forms 3 or sometimes 4 if it carries a charge. Oxygen forms 2, and all the halogens fluorine, chlorine, bromine, iodine, iodine, right? Iodine form 1 bond. These numbers are your rules for drawing valence structures. So yes, as you can see, hydrogen forming 1 bond, carbon 4, nitrogen this, then 2, right? So the number of covalent bonds as shown here, right? So that's the structural theory of organic chemistry. Summarize: carbon is tetravalent. It always forms 4 bonds. Oxygen is divalent. It always forms 2 bonds. Hydrogen and all the halogens are monovalent. They form 1 bond each. Look at the structures on this slide, right? So as you can see, these are the structures. The dashed lines indicate the bonds, right, that they can form. So oxygen has 2, nitrogen 1, hydrogen 1, bromine 1. Yes, so they are monovalent, divalent, tetravalent. Yeah. So each one obeys these rules, right, perfectly. When you draw organic structures, always check, does every carbon have exactly 4 bonds? That's the question, right? So it means if you have more than 4, means something is wrong, right? Something is wrong. So carbon has 4 bonds. This is critical, right? And worth repeating. Never draw a carbon atom with more than 4 bonds. Right? As I said earlier, look at the examples on this slide. A carbon with 4 bonds is correct, right? Yeah, that's correct. 5 or more bonds on carbon is chemically impossible under normal condition. If you ever find yourself drawing 5 bonds on carbon, stop. Something is wrong with your structure. Yeah. So as I said, that is very very important. Right? Make sure you don't exceed, right? You don't exceed more than 4 bonds, right? So yeah, these are the various ways of representing the bond, right? Can form double bond and two single bonds, or 4 single bond throughout, and can form what, 1 triple bond and 1 single bond. Yeah, those are the 4 bonds. Yeah. Now, what if carbon has only 3 bonds? That's possible, yeah, but it requires a formal charge on the carbon atom. For example, a carbocation has 3 bonds and a positive charge, right? That means it has lost an electron, yeah, a valence electron. A carbon anion has 3 bonds and a negative charge. That means it has gained what? An extra electron. These are reactive intermediates you encounter throughout the course. And to reiterate, never draw 5 or more what, bonds on carbon ever. Yeah. So that's okay. Yeah. Oxygen, as we said, is usually divalent. It forms 2 bonds. Look at these examples. In diethyl, oxygen bridges 2 carbon chains. In methanol, it connects to 1 carbon and 1 hydrogen, right? And then um, in acetone, it sits as a double bond to carbon, right? The carbonyl group, no matter the structure, oxygen almost always has exactly 2 bonds. Yeah. So yeah, because here, here, and here. Yeah. However, oxygen can form 3 bonds when it donates its lone pair electrons to a Lewis acid, a concept called a dative covalent bond. Yeah. When this happens, oxygen carries a positive charge, right? Look at this example, methanol. right? Methanol, you can see methanol, yeah, reacts with a proton, and the oxygen accepts H plus, right, forming a positively charged species with what, three bonds on oxygen. Yeah, this is completely legitimate as long as the charge is shown. So that, as you can see, this is H plus, and oxygen is accepting that. When I accept that, there is what, positive charge here, a positive charge here, and there is a dative covalent bond that's formed. Yeah, dative covalent bond that's formed. Here is another example: acetone reacting with bromine fluoride, that's BF3, a classic Lewis acid. BF3 has an empty p orbital on boron, making it electron deficient. The oxygen um, in acetone donates 8 lone pair into that empty orbital shell, forming a dative bond. The result is a Lewis acid, a base what adapt. This is a preview of Lewis acid base chemistry, which we will revisit in detail. Yeah. Conversely, when oxygen has only one bond, it carries a negative charge. You will see this in alkoxide ions. For example, the reaction of an alcohol with a base removes the OH proton, leaving a negatively charged oxygen with just one bond to carbon. Always pair the reduced bond count with the appropriate charge. So yeah, this is the reaction shown, right? And this is an alkyl group, like the R. It represents a certain compound group. Yeah. Now let's talk about isomers. Isomers are different compounds, right, that share the same molecular formula. Look at these two molecules, one butanol and diethyl. Both have the molecular formula C4H10O, yet they are completely different compounds with different structures. Yes, so they have the same molecular formula. That's what, C4H10O, right? O. However, if you look at the structure, you could see that the structures are different, right? The structures are different. So that makes them isomers, but they have the same molecular formula. Yes. These two compounds, one butanol and diethyl, are constitutional isomers. They have the same molecular formula but different connectivity of atoms. But yeah, different connectivity. And because the connectivity differs, their physical properties differ dramatically. Different boiling point, melting point, and densities. Yeah, densities. Their chemical reactivities also differ. This is why structural formulas matter so much. Molecular formula alone is not enough. So we need to look into the structural formula. That's the most important thing. Right? So the formula, as I stated earlier, is was there, and then the constitutional what, isomers. Yes. So basically that's it. We now arrive at one of the most fundamental principles in chemistry, the octet rule. The octet rule. There are two main types of chemical bonds: ionic bonds formed by the transfer of electrons from one atom to another, creating ions, and covalent bonds formed when atoms share electrons. The octet rule says that atoms tend to gain, lose, or share electrons to achieve a stable configuration of 8 valence electrons. Yeah. So that's basically what the octet rule is saying. So the ionic what bond and the covalent bond is that's what they are here, right? Okay. Um, so yes, when the octet rule is satisfied, right? For carbon, nitrogen, oxygen, and fluorine, they each achieve an electron configuration analogous to the noble gas neon, right? The noble gas neon, with 8 electrons in the outer shell. This is energetically stable configuration these atoms strive for in chemical bonding. The octet rule is your guide for drawing valid Lewis structures. Yeah. So the most important thing, the octet rule is a very important thing to consider as far as organic chemistry or bonding is considered. Let's review noble gas uh, configurations. Helium has 2 electrons in its only shell, right? This is what hydrogen aims for, right? This is what hydrogen aims for. This is what neon has what 8 electrons in its outermost shell. This is what carbon, nitrogen, oxygen, fluorine strive for. Argon also has 8 what outermost shell. Understanding this configuration, right, tells you exactly how many electrons each atom needs to what gain, lose, or share. So as you know, right, hydrogen, if you draw the configuration, yeah, it has what 1 electron. So when it gains an extra one, it becomes 2. So that makes it what helium like. That's why I have 2. So hydrogen aims for 2 outer shell, right? Outer shell electron. Then neon, which is 8, right? Um, Argon is 8. So for the neon, if you have carbon like this, right? So carbon has like I think 4. Yeah, so carbon has 4 valence electrons. So it will need extra 4 to make it what 8. Yeah, so that makes it achieve a similar structure like neon. And then yeah, similar for nitrogen, oxygen, and fluorine, right? Then argon to yeah, similar trend. Let's now look at ionic bonds in more detail. Atoms can gain or lose electrons to form charged particles called ions. A cation is positively charged. It has lost electrons. Yes, so that's the definition of cation. Cation as positively charged. Right? Yeah. And then anion is negatively what charged. That means it has gained what electron or electrons. Yeah. An ionic bond is the electrostatic attraction between oppositively what charged uh, ions. Ion bonds are Ionic bonds are common in what inorganic chemistry and they do appear in what organic chemistry, especially with charged what intermediate. So if you have something like sodium chloride, right? Sodium chloride, it's made up of sodium plus and what chlorine what minus. So that makes it an ionic bond, right? And these are actually considered mostly in what inorganic chemistry. But for organic chemistry, you can have some organic compounds that are charged, right? They are charged. Yes. Before we look at covalent bond, we need to understand electronegativity. Electronegativity, abbreviated EN, is an atom's intrinsic ability to attract shared electrons towards itself in a covalent bond, right, is measured on an arbitrary scale. Fluorine is the most electronegative element with En equal to 4, and cesium is the least, that's what, 0.7. The larger the electronegativity difference between two atoms, the more polar the bond between them, right? Yeah. So electronegativity basically increases as you move from what, left to right, right, from left to right. Um, yeah. So as you can see from the figure here, here are some key electronegativity values you should know. So carbon is 2.5, nitrogen is 3, oxygen is what, 3.5, fluorine is 4, hydrogen is 2.1. The halogens range from what, 4 to what, like that's 4 for fluorine down to a 2.5 for iodine. So as you can see here by the what, the blue arrow, right, pointing upwards here. Notice that alkali metals on the left as lithium, sodium, potassium have very low electronegativities, meaning they readily what, give up electrons, right? These values predict bond polarity, which drives reactivity. Yeah. So as I said in the previous slide, the red arrow, right, indicate that as you move from left to right, electronegativity increases, right? And then as you move from what, down to the top, electronegativity what, increases generally. Yeah. So basically that's the trend for electronegativity, right? So you guys can try and what, uh write down here. Maybe you can practice with these values, right? Practice with these values. So now let's see ionic bonding in action, right? For the previous example that I used, right? Yeah. So this is a classic example: sodium and chlorine. Sodium has one electron in its outermost shell. Yeah, one electron in its outermost shell, as you can see here, 3s1. Yes. Um, it wants to get rid of it. Yeah. Then chlorine has 7 electrons in its outermost shell. It needs just one more to complete its octet, right? So sodium donates it, right? It donates its what's it called? Donate its electron to chlorine. Now sodium carries a plus one charge, right? Sodium carries a plus one charge, as you can see here. Chlorine carries a minus one charge, as you can see in the diagram, right? Yeah. So the electrostatic attraction between them forms the ionic bond of what? Sodium chloride. So when that happens, there is this electrostatic attraction between them, which form the sodium chloride. That's NaCl. Um, so that is a typical ionic bonding in action. Ionic bonding in action. Now let's look at covalent bond, right? Lewis structures. Covalent bond in Lewis structures, right? Yeah. Covalent bonds form when atoms of what, similar electronegativity share electrons rather than transfer them. Yeah. In covalent bonding, both atoms contribute electrons to a shared pair, and by sharing, both achieve noble gas configuration. Yeah, so as I illustrated earlier, so both achieve noble gas configuration. Molecules held together exclusively or predominantly by covalent bond are the heart of organic chemistry. Lewis structures are a way of representing these bonds on what paper. So look into that. Yeah, look into that. So here is a covalent bonding illustrated with two chlorine atoms. Right? Each chlorine has the configuration that's what for neon and what 3s2 3p5, meaning seven valence electrons. Neither atom wants to give up an electron entirely because they have the same what electronegativity. Yeah, so they have similar electronegativity. So instead, right, they share one electron each. They share one electron each, forming a single covalent bond. So Cl minus, right, Cl. So as you can see here, so Cl, Cl. So when they share like, let me just draw like structure. So this one bring one, and this one to also bring one, right? Yeah. So they share the electrons, right? They share the electrons to obtain the octet rule, right? So with that, each chlorine now effectively has 8 electrons in its outer shell, satisfying the octet rule, right? And then the non-bonding pairs are shown as what lone pairs. So if you look at this, they have what 3 lone pairs, right? So when you say pairs, means they come in two, so in double. So each of them has 3 lone pairs. Ions themselves can contain covalent bonds, right? Consider ammonia, that's NH3. Nitrogen forms 3 covalent bonds, right? Forms 3 covalent bonds with hydrogen and has 1 lone pair. When a proton H plus approaches nitrogen's lone pairs, forms what? A dative bond with the proton. The result is the ammonium cation, that's NH plus, where nitrogen now has 4 bonds and a positive charge. This is an excellent example of how dative bonds and formal charges work together. Uh, So as I've tried to explain with the diagram, right? As I've tried to explain the diagram. So the arrow here indicates that the lone pair is being donated to the H plus, which has no what electron. So it will occupy it, and then now the nitrogen have what a positive charge, and then yeah, ammonium cation is formed. Ammonium cation is formed. So yeah, ions can have what? These ions can have what? Covalent bonds as well. Yeah. Now we enter one of the most important topics in this course, hybridization. Let's start with sp3 hybridization. In its ground state, carbon has electron configuration of what? 1s2, 2s2, 2px1, 2py1, and then 2pz0, right? Yeah, this means carbon has only two unpaired electrons, which would suggest it forms only 2 bonds, right? But we know carbon forms what? 4 bonds. The explanation is what? Hybridization. Yeah, hybridization. As you can see, there's a diagram. The diagram. So yeah, when carbon forms 4 bonds, right, the 2s orbital and all three 2p orbitals but mix or hybridize to form 4 equivalent sp3 hybrid orbitals. The sp3 name tells you the composition: 1s orbital, 3p orbitals combined. Yeah. So that's what it's trying to say. Each sp3 orbital holds one electron, and each forms a sigma bond with hydrogen. This is exactly what happens in methane, that's CH4. That's what the diagram is basically trying to see. So that's what I've explained. Right. That's what I've explained. The four sp3 orbitals of carbon are arranged in a tetrahedral geometry. So this one, inorganic chemistry will tell you that. So bond angles of approximately 109.5 degrees. That's what inorganic chemistry will say. This means the hydrogen in methane are not in a flat plane, but arranged in three-dimensional space around carbon like what, a four-sided pyramid. Yeah, around carbon like a four-sided. So if you have the carbon, you can have something like this. So it's like a pyramid, right? It's like a pyramid. Like, that's what from the tetrahedron. Tetrahedron, like a pyramid. Yeah. Yeah. So this is the 3D reality of organic molecules, and you need to be comfortable visualizing it. Yeah, because you will need this. The 3D structure shown here use solid wedges for bonds coming toward you, and dash wedges for bonds what, going backward. So if the bond is pointing toward you, it has what, solid line or dash line, right? And then the solid, yeah, wedges. That's the deep one. So that's the line, the deep line, right? And then the one that is showing like dash wedges, those show that the points are pointing away from you. Yeah, they are pointing away from you. Yeah. Yeah. So this slide shows detailed representation of methane, right? Methane. So take a moment to look at each representation. The restructure, the 3D ball and stick model, the space filling model. Notice how all four bonds points symmetrically outward from carbon in a perfect tetrahedron, right? So this symmetry means methane is nonpolar even though each CH bond is what, slightly polar individually. Yeah, it's polar individually. So look at this structural diagram. So this represent the what? Yeah, yeah. So this represent the sp3 hybridized carbon in methane, showing the tetrahedral arrangement in three dimensions. So as I said, so you see it's looking like a pyramid. Yeah, it's looking like a pyramid. Yeah. So the angle between any two bonds, as I said, there is what, 109.5 degrees. That's the ideal tetrahedral what angle. So sometimes some charges can cause the angles to shift, right? So which we look at it. I mean, it will be well appreciated in inorganic chemistry. And here is another view of the same methane structure. So chemists use multiple representations because each highlights different features. So here is what ball and stick models emphasize what, connectivity. Space filling models emphasize the actual volume occupied by what, atoms. So for example, you mostly use dash structures and wedge and dash what structures. Yeah. So here is a model. Yeah. So this 3D model But representation captures the true shape of what methane, right? Yeah. So notice that no two hydrogens are directly opposite each other. So are directly opposite each other. So the hydrogen, they are not really opposite each other. They are not really opposite each other. So then the black one indicate the what? The carbon. The carbon. Yeah. So they are spread equally around the carbon at what 109.5 degree angle. This is the direct what consequence of four equivalent sp3 orbitals minimizing electron repulsion. Now, yes, let's extend sp3 hybridization to ethane as C2H6. Yeah, ethane. So ethane has two sp3 carbons, each carbon eh, each bonded to three hydrogens and to each other, right? So each of them is bonded to three hydrogen and then to each other. Yeah. So the CC single bond is a sigma bond. That's a direct overlap of sp3 orbitals. Then both carbons maintain their tetrahedral geometry. Ethane can freely rotate around the CC single bond, and we will explore the energy consequences of that rotation when we discuss conformational analysis. Yeah. So we discuss that. Um, Study this diagram too. Yeah, study this diagram of ethene. So notice how each carbon has a tetrahedral arrangement and the CC single bond connects the two carbon centers. So rotation around this single bond is relatively free. It's relatively free. So when we rotate this one, it's relatively free. It requires only about 13 to 26 kilojoules per mole to rotate, which is very low energy. So this one in inorganic chemistry, you will realize about the how much energy that required to rotate this. Now we move to sp3 hybridization seen in ethene, right? So that's double bond there, also called ethylene. In sp2, so yeah, in sp2 hybridization, the 2s orbital mixes with only two of the three 2p orbitals, right? Producing three sp2 hybrid orbitals and leaving one unhybridized what p orbital. Yes. So the three sp2 orbitals form sigma bonds in a trigonal planar arrangement with bond angles of what? Yeah, approximately 120 degrees. The remaining p orbital is what? Perpendicular to this plane, and it participates in forming the pi bond. Yeah. So that's what basically the diagram is saying, right? So the explanation that I've made, that's basically the diagram is saying. So yes, so here is the 3D structure of ethene. The two sp2 carbons and all four hydrogens lie in a flat plane. Ethene is planar. Yes, ethene is planar. The pi bond forms by sideways overlap of the two unhybridized p orbitals. So one from each carbon. This pi bond sits above what and below the plane of the molecule. So as you can see, so they sit above and below the plane of the molecule. So this is the plane. I mean, that rectangular shape is, and that's the plane. Yes. So the pi bonds are here. This one of them, and this the one below. Like one below. Yeah. So together, the sigma and pi bond form the carbon-carbon double bond. So a carbon, that is C, yeah, the C double bond, right? C, right? Bond consists of one sigma bond plus what? One pi bond. So the double bond, one of them is pi and one of them is what? Sigma. Yeah. So yeah, let's look at this diagram. Let's look at this diagram. You could see that um, the p orbitals on each carbon are what aligned parallel to each other, and they overlap laterally to form the pi bond. Uh, Overlap laterally to form the pi bond. Um, yeah. So this sideways overlap is weaker than the head-on sigma overlap, which is why pi bonds are the reactive sites in what alkenes. So they are more accessible to what reagents. And then yes, let's see this diagram too. So these additional representation of ethene reinforce the what planarity and the pi electron density, right? So notice how the what electron density of the pi bond is spread above and below the what the molecular plane. So this is where electrophilic reagents will attack. Yeah, where electrophilic reagents will attack. So yeah, this space filling model shows the actual volume of ethene. The molecule is indeed flat, right? So the molecule is indeed flat. Um, and also, you can see the electron density distributed symmetrically. This physical shape has real consequence for reactivity, and reagents approach the pi bond from above and below the plane. Yeah. Uh, Here is another rendering of ethene. Take a moment to visualize the planarity. Um, all six atoms in the same plane. So yeah, this planarity is a direct result of what sp2 hybridization. Then study this diagram too as well. You notice that the geometry here, the H, that is HCH. As you can see here, this side, ACH bond angle, and the HC double bond angle are both approximately 120. Right, approximately 120. Um, yeah, approximately 120. And this slide also summarizes the key features of sp2 hybridization in ethene. So trigonal what planar geometry, 120-degree bond angle, and a pi bond formed by what lateral p orbital overlap. So keep this what mental image. You use it every time you encounter a double bond, right? The double bond. Oh, okay, okay. So now a critical consequence of what of the pi bond. That's restricted rotation. Restricted rotation. Okay. Unlike single bonds, you cannot freely rotate around a carbon-carbon double bond. The pi bond requires the two p orbitals to remain parallel. If you rotate them 90 degrees, the pi bond break. So the energy barrier to rotate around a double bond is approximately 264 uh, uh, kilojoule per mole, right? Uh, kilojoule per mole. So the strength of the pi bond itself, that's the strength of the pi bond itself. So compare this to rotation around carbon-carbon single bond, which costs only 13 to 26 kilojoules per mole. This enormous difference has a profound uh, consequence. That's the geometric isomerism. So yeah, it's not really easy to rotate around double bond. So yes, this illustrates the energetic cost of rotating around a double bond. The eclipse conformation, where pi bond is breaking, sits at the top of the energy barrier. At room temperature, this barrier cannot be overcome by thermal energy alone. As a result, groups on either side of a double bond are locked in place relative to each other. Yes. Um, yes, because rotation around double bond is restricted, we get a new type of isomerism. That's the cis-trans isomerism, also called geometric isomerism. Look at the examples on this slide. When both substituents on one side of the double bond are the same, or when we have identical groups on opposite sides, the molecules can exist as distinct isomers. These isomers cannot interconvert without breaking the pi bond. Yes, so as you can see, those are the cis trans isomers. These are the diagram, right? So these are the diagram. These are the diagrams. So here we see a simple but clear example. 2-butene. The cis isomer has both methyl groups on the same side, right? On the same side of the double bond. Then the trans isomer has them on opposite sides. So this is the cis. You could see that the CH are on the same side, and then the trans, right? The opposite side. Yeah. So these are different compounds. They have different physical properties and can be isolated separately. This slide emphasizes the same molecular formula, the same connectivity, but different spatial arrangements. Yes, so let's look at name examples. Trans 1 bromo 2 chloroethene has bromine and chlorine on opposite sides of the double bond. Yeah, so as you can see, that is a trans. And then says 1 bromo 2 chloroethene. So ethene. So that's also there. Yeah, so the naming rule here is straightforward for 1, 2 dice substituted what alkenes. Identify both substituents, then use cis or trans depending on their spatial arrangement. We use this system extensively when we cover alkene nomenclature. Alkene nomenclature. So here are additional examples: cis and trans 3-hexene and cis and trans 1,3-dibromopropene. Notice that the cis-trans naming system works well when there are only two different groups on each carbon of the double bond. When there are more complex substituents, we will use the EZ system instead, which we will cover later in the course. Now, our third hybridization type, sp hybridization seen in Ethyne, also called acetylene. In sp hybridization, only the s orbital and one p orbital mix, producing two sp hybrid orbitals, right? So yeah, the other two p orbitals remain unhybridized. The two sp orbitals, right? The two sp orbitals form sigma bonds, one to hydrogen and one towards other carbon. Yeah, to other carbon, giving a linear geometry with a bond angle of exactly what 180 degrees. So the two unhybridized p orbitals on each carbon overlap to form what two pi bonds. So combined with the sigma bond, this gives us the carbon-carbon triple bond. One sigma plus two what triple bond. So yeah. So for each uh triple bond we have what one sigma bond and what two pi bond. Yes, that's from the linear structure. So yeah, let's look at this diagram, right? So of ethine, yeah. So yeah, the two sp orbitals point in opposite direction, giving the what the linear geometry. So the two sets of p orbitals, one pair in the vertical direction and one in the horizontal, each form a pi bond. So there are actually two perpendicular pi systems in triple bonds. This is why alkynes are even more what electron rich than alkenes. Yeah. And let's study this structure too. Here you can see the linear arrangement of atoms in ethine. So HC, AC, triple bond C, H, right? All atoms in a straight line. This, um, yeah, so this linear geometry is a direct consequence of sp hybridization. Notice the triple bond shown between the two carbons. Yeah. So the 3D model of ethane reinforces its linear rod-like shape. The triple bond is shorter and stronger than a double bond, which in turn is shorter and stronger than a single bond. Yes. So the carbon-carbon triple bond length is in ethane is 1.2 angstrom. That's 10 to the power minus 10, compared to 1.34 for carbon-carbon double bond and 1.54 for carbon-carbon single bond. So yes, here is an important relationship between hybridization and orbital character. So an sp orbital has 50% s character and 50% p character. An sp2 orbital has 33% s character and 66% p character. An sp3 orbital has 25% character and 75% p what character. So why does this matter? So greater s character means the orbital is held closer to the nucleus, right? Making it lower in energy and more electronegative. This directly affects acidity, right? So sp-CH bonds are more acidic than sp2-CH bonds, which are more acidic than sp3-CH bonds. Yes. So let's take stock. Uh, we've covered three types of hybridization: sp3, uh, that's four equivalent bonds, tetrahedral geometry, 109.5 degree angles, seen in alkenes, right? Alkenes, sp2, three sigma bonds plus one pi bond, trigonal planar geometry, 120 degree angles. Yes, 120 degree angle. I mean 121 to is so there. Yeah. and seen in alkenes. Yeah. And then sp, two sigma bonds plus what? As the sp. Yeah, two sigma bonds uh plus two pi bonds. Linear geometry, 180 degrees angles seen in alkynes. These three geometries define the shape of what? Virtually every organic molecule you encounter. Yeah, the molecule you encounter. Now let's turn to something very practical. How to read and write structural formulas. Organic chemists use several, organic chemists use several types of structural representations, each with different levels of detail. We will cover four: dash structures, uh, condensed structures, bond line structures, and three-dimensional structures. Knowing how to move between these representations is an essential skill. Yeah. The most explicit representation is the Dye structural formula, also called the Lewis structure or full structural formula. Every atom is shown, and every bond is represented by a dash, right? So lone pairs are sometimes shown. This is the most informative representation, right? But also the most time consuming to draw. Notice the examples of propyl alcohol shown in different orientation. They all right, they all represent the same molecule because single bonds allow free rotation, as discussed earlier. Atoms connected by single bonds are simply rotated to make the drawing convenient. Convenient. Condensed structural formulas. Yeah. Save space by what? Grouping atoms together. Instead of showing every CH bond, we write CH3, CH2, or CH with the hydrogens implied. For example, ethane becomes what? CH3, CH3. Um, as you can see, CH3, CH3. Okay. This format is very commonly used in textbooks and on exams. The key skill is knowing which hydrogens are hidden, right, and how to expand a condensed formula back into a full structural formula. So yes, so as you can see, these are like expanded formula, right? And these are the condensed forms. And the condensed form, it has a safe space, right? So you can see the most commonly used shorthand in organic chemistry is the bond line formula, also called the skeletal structure. In this system, carbon atoms are represented by the vertices and ends of what? Zigzag lines. Right? Hydrogens on carbon are completely omitted, but you know they are there because carbon must have four bonds. Right? Yes. Only non-carbon atoms and heteroatom attached hydrogens are shown. For example, a straight chain of six carbons appear as a zigzag with what? Five line segment. Five line segment. So it's like this. One, two, three. So one, two, three, four. Four here and then outward. So yes. So this is hexane. Hexane, one carbon here. I have one carbon here, another here, another here, another here. another here. So this is 1, 2, 3, 4, 5. Okay, so 6 will be here. So yeah, 6 carbon. So that's how you can represent something like hexene. That's 6 carbon. So these bond line formulas represent various organic molecules. Uh, so practice reading each one. Count the vertices. Remember that each vertex is a carbon, and add hydrogens mentally to what bring each carbon to 4 bonds. This skill becomes second nature with practice, but it requires deliberate effort at first. Count the carbons and what hydrogens in each structure shown here. So we can count them. Finally, three-dimensional structural formulas. Use a convention of solid and dash wedges to convey depth. A solid wedge represents uh, a bond coming towards you and out of the plane of the page, and a dash wedge represents a bone going away from you into the plane of the page. Yes. So regular lines represent bonds in the plane of the page. Look at the examples. Ethene and bromomethane drawn with this 3D convention. You use these constantly in stereochemistry. Yeah. Stereochemistry. So the dash line represent that the hydrogen is pointing away from you, and then the solid one represent that it's pointing towards you. Yes. So here are just further examples of 3D structural formulas, including cases with trigonal, planar, and linear geometry. Notice how the wedge and dash notation captures the three-dimensional reality of these formulas, molecules. For trigonal planar sp2 carbons, all bonds lie in a plane. For linear sp carbons, we use a straight line. Mastering these representations is essential for upcoming topics in stereochemistry. So, yes, that brings us to the end of lecture one. We've covered the the foundational concepts in organic chemistry. Our next topic, we'll dive a little bit deeper into organic chemistry. Thank you, and stay tuned for the next um, topic on organic chemistry.